So today 1 hour and just online, not hybrid. Actually, yesterday I didn't know that online. Okay, so now let us start. Okay, another 8 students. Okay, now let me start. Bismillah, recording first. Okay, sharing screen. And please, you can register first. Okay, today I have prepared the quiz 1 fully ready, and some students are really solve it well, and but many students not very good. I didn't expect that you can fail from the quiz 1. Quiz 1 was very simple, very easy. Okay, now next week I will announce the quiz 2, then both of them I will put in the e-pembelajaran. Okay, could you register?
Yes.
Okay. So now let me show your results first. Just I do the screening. I put, after finishing the second one, I will finish. Actually, this one over 10. Huh? Currently, this is over 10, but I will, yeah, over 10. I will reduce by 2. You see, there's some students very, very bad. So actually, this one is actually 0. Just I put. So you can see this is your mark. You see there is 8. Nobody could get the 10 because, you know, for the marking, I have some schema. According to the schema, you see some students got 0, which is 1 is a 0 mark actually. You see 3, 5, 9 or 8, 9 also you have, but not many. Okay, there is some 9. Okay, Alhamdulillah, all the students attended. None of them left the first quiz, 100% attendance. Okay, so please do your best. Now second quiz, I will see how much you got it. Now, Miss Anne, please you collect the group, the group of the students, 12 groups. 12 groups. Each groups need to be 5 person in each group. Okay, and I will this coming Sunday I will show you how to do the assignment. Okay, so I have to construct some more questions. Still not finished it yet. Today I cannot announce, but the next Sunday I will announce. And this week I'm not going to. This week is week 8 or week 9. This week 9, huh?
This week,
Or week 8?
This week, week 8.
Week 8. Ah, okay. It's week 8. So not next week. After following week, the week 10, the midterm exam. Okay, midterm exam will be on 10th of week. So 8, 9, 10. Okay. Yeah, you have enough time, and I have to finish the chapter 3 because it contains mostly chapter 2 and chapter 3. Okay, because chapter 1 maybe I include, but maybe not include, because chapter 1 includes the final exam. Final exam includes all actually. So mostly chapter 2, chapter 3, I focus on chapter 2, chapter 3 for final the midterm exam, and chapter final exam actually includes all chapter 1, 2, 3, 4. It is already ready. We have constructed everything done. Okay, so this is your mark again. Please look who get 1. Actually, it is 0. So just I gave the 1 mark. So which means none of the questions is not correct. This is not good, not good. So actually here midterm exam 20 mark, 20 mark, assignment presentation 25, 20, 25, 45, and 15. Quiz 2 actually 10 mark. This one is a 5 mark. I will reduce into the 5 marks. So insert. So if I make it 5 marks, which is I divide previous mark into 2. Okay, so this one is your real mark. Okay, so results not very good. Please improve your knowledge on this subject is very okay. So the second one is actually not MCQ. It is subjective, because this time I got previously I make it MCQ, but this is subjective now. Subjective. Okay, total will be 15. Yeah. Okay, done. So this is your mark. Okay, let me start. Please, who did us 2 more people in the lobby? Please do sign the register first. And let me start today. Actually, I want to show some extra informations. Where is my lecture? Already I close it. Okay, I should open again. Just now I suddenly close. Okay, note chapter 3. Chapter 3. Okay, now generally, as I told you, so this theorem is one of the main theorem. So every point you should understand what is the isolated point is already clearly stated, and gave examples, many examples. Then what else we have learned? Open set. Now we are coming to the closed set. So once open set is clear, then closed set we will discuss now. And of course, this open set actually has these 3 properties. You see, the empty set and R is open set, open sets. Any intersection of finite number of open sets in R is open. Already we have proved this proof. Any union of arbitrary collection, you see, any union of arbitrary collection. Here, any intersection of finite number of open sets. Here, any union means infinitely many the union of the sets, collection of the sets, arbitrary collection of open sets in R is open. So now this one we have proved it. Next, this is good example to understand that if given set are open set, then when we collect the intersections, If this intersection is finite, then the collection of finite intersection of the open set is open set. Otherwise, this is good example. This is counter example that if I say any collection of the any intersection of arbitrary collections, you see, arbitrary collection of the open sets in R is open is wrong. This is counter example. You see, intersection gives 1 point. 1 point is not open set. Okay. Okay. Next. Now, what about closed set? You see, definition says, let F be the subset of real numbers. Then F is said to be closed if it is complement is open set. Theorem, next theorem, a subset F of R is closed if and only if F contains each of its accumulation points. So in other words, F is called closed set if it consists of F plus additional the accumulation points. So if F is called closed if it consists of all collection of accumulation points. Okay, you see, all each means all, each of its accumulation points. And what does it mean? Complement. Here there is one very nice and clear definition. I searched some PDF file, but there is no PDF file. Maybe I will just make copy and make the PDF file. So what does it mean? Complement. Complement of the set. A well-defined collection of objects or elements is known as a set. This is the set definition of the. What is a set? Set is a collection of the objects or here elements. Objects or elements. It is called set. Any set consisting of all objects, please pay attention. Any set consisting of all the objects or elements related to the particular context is defined as a universal set. So universal set actually is the big set. Any set consisting of all objects related to the particular context is called universal set. It is represented by U. For any set which is subset of universal set is actually any set, this one is a confirmation, any set is a subset of the universal set. The complement of A, of the set A, consists of those elements which are member or elements of the universal set U, but not of the set A. Symbolically, here there is a symbolic notations. Where is complement? This is intersection. Complement of the set. Actually, it is not given as diagram, but complement. You see, the complement is a set where the consists of all the elements where not belong to the A. Not belong to the A. For example, if U is 1, 2, 3 up to 10, A 1, 2, 3, 4, then A prime becomes so the A prime, actually not A prime, usually AC. 1, why here 1, 6? No, here something wrong. 1 is already here. It should be not in A, but in U. So if I subtract this 1, 2, 3, 4, it should be 5, 6, 7, 8, 9, 10. Oh, here's something wrong in this example. Something wrong. This is difference of the sets. Actually, please you here A prime. You see, this is a prime actually is out of A. All the elements not belong to the A, but under U. So we have to construct the U first. Okay, U should be given universal set. So it is within the U, but out of the U, A. And here there is interesting properties. There is properties of the complement set. Look, first, the union of the set A and its complement gives the universal set. See, A union A prime gives the universal set. Intersection of A and A complement is empty set. Look here. This is the U universal set. This is A, 1, 2, 3. This is 4, 5. A prime is 4, 5, according to this. So A union A prime gives 1, 2, 3, 4, 5, which is U. Okay. So there is interesting properties. A plus union A prime or AC complement is equal to U. And intersection of these two sets are empty sets. Another property is complement of the complement returns to the A. You see, double prime gives actually A. This is another properties. Complement of the set. This is examples. You can learn it, no problem. And as I think that's the main properties. Currently, 3 properties. So A union AC is equal to U universal set, but A intersection A prime is an empty set. Okay, that please just revise all this type of kind of set theory. You just revise what is a complement of the set. Complement of the set is the set such that it is out of the A but under the U, the universal set. It should be under the universal set. If universal set not given, just given A, so you will say that it is infinitely set of out of the A. For example, here also they have given. So definition, if you see now definition of the closed set. Okay, definition of the closed set. It is said F is said to be closed if its complement is open. Okay, because of this definition, you will see this theorem is correct. Is correct. Okay, look, after this, just look at this. Close subsets of the real numbers. Now, what is the definition of the closed set? Closed set is the set such that FC, the complement, is open. If complement is open, then F is closed. Opposite, if FC is closed, then F is open. Vice versa is also true. Okay, so under this definition, actually this theorem is correct because look, the first one, closed subsets of real numbers have the following properties. The set empty set and R are closed. Why? Because the complement of empty set, you see, this proof is really based on the very simple and nice solution of the definition. So what we call it, the proof of the theorem 1-3. I don't want to state, so blah blah blah. So the part A, how we prove. So consider this the empty set, and find complement. Actually, not better. We say C. C because F prime. If you remember, F prime is the set of the accumulation points. All the accumulation points is called a derived set, denoted by F prime. So F prime is a collection of accumulation points. So that's why. So we should say different. The complement of F of phi of empty set is R. R is open set. Once R is open set, according to the definition, so phi is the empty set is closed. You see, and the second one is also used. Now I consider R set R. The R complement is empty set. Empty set is open set. Open set. Therefore, from this I can conclude R is closed. R is closed. In the previous theorem, TH 1.2, it is said empty set and real number set are open set. Open set. And we have shown this R is open set because open set because of every point, because of, you see, every point, I mean the epsilon neighborhood of x minus epsilon x plus epsilon is a subset of R. Then the collection of all these these intervals gives that the R is open set, right? R is open set. We have proved this one. Okay, you see, both theorem, it looks like contradictory each other, but both of them are correct according to the definition. Okay, so that's why please pay attention. So now, regarding to the closed set, another two things I didn't prove because I gave you this one as a homework, and here proof is very simple and clear. This one is much more clear than the first theorem. Okay, in the first theorem, we have to show that, take the element, then show that this element belongs to the next set. Here, we just use De Morgan's law. De Morgan's law. You see, De Morgan's law says the union of the sets, complement of the union of the sets equal to intersection of the complement of each sets. And this is a finite. This is a finite. This set is open set. So if complement is open set, then F is closed set. Okay. For the C, arbitrary intersection of any intersection of arbitrary collection of the closed sets. Here, the finite number of closed sets. The union, any union of the finite number of the set is closed. Any intersection, you see, here intersection opposite, infinitely many. Any intersection of an arbitrary collection of closed sets in R is closed. Proof, opposite. We consider the complement of F, which is intersection, you see, gives the union of C alpha. And according to the previous theorem, any union of arbitrary collection of open sets is open set. Since this one is open and it is a complement of F, so F is closed. So very nice proof, okay? And here there is the one more example. You see, this example also shows very nice, you see, very nice, this example provides us the counter examples of the wrong theorem. For example, if I say here, any union of not finite, any union of arbitrary collection of closed sets in R is closed. Just instead of finite, I say any arbitrary collection of the closed sets in R is closed. this one good example, counter example of that one. Okay, let me show you how they actually it is here. They just put like this. So I will prove more properly. Example, maybe I can say two previous example. So for each n, problem say for each n from capital N, the natural number set, we consider this set A. Actually, AN, I can say 1 over N and 1. You can see it is closed set. For each N is closed set. Is closed set. Now, I will consider the first, I will consider the finite union of this. So, Sn is a finite union of An, Fk, Ak, K from 1 to N. So if I take the N equal to 1, 1, 1. 1 is actually 1 point. It is not interval, but I just write as 1 over 2, 1 over 2, 1. Close it. Union 1 over 3, 1. And etc. Up to N. So here I just state union and etc. union 1 over N 1. Okay, what about the union of this? This element, one element, if I add with this one, it will be 1 over 2, 1 over 2, 1. Then union, this is one element, 1 over 2, union, 1 over 3, 1. Union, and etc. Union, 1 over N, 1. Okay? So 1 over 3 is below to 1 over 3. So it becomes 1 over 3. And etc. etc. If I collect like this, so 1 over 3 is bigger than this set. The next one is bigger than the previous set. So at the end, I will get 1 over N and 1. You see, this is the finite collection of the closed sets. Finite collection. Okay, finite collection currently is closed set. It is okay. Now I will consider the limit. Limit Sn. Sn tends to infinity. What does it mean? If I go to like this, so this one k from 1 up to infinity ak. And if I take the limit from this, you see, when n tends to infinity, this part becomes not closed, becomes open because of limit, you know, we will get like this. Now this one is not closed, is not closed. So that's why the arbitrary union of the sets may not be closed set, but finite one is closed. So that's why in this theorem they say finite, the union, any union of finite number of the closed sets in R is closed. But any intersection of the arbitrary collection of the closed sets in R is closed. Okay, so please pay attention that this is a proof of actually this is an example of the confirmation of the above theorem. If wrong formulation, because of this example, I can say that it is wrong. Okay, counter examples we have this is good counter example to the wrong statement. Okay, next is So currently, I think everything is clear, huh? Because uh, in this situation, so we are talking about the properties of the closed sets. So please pay attention. A closed set is a set such that it contains all the accumulation points. Okay, all the accumulation points. Now, this closed set has three properties. Any the empty set and or a closed set, and union of the finite. Any union of finite number of closed set is closed. Any intersection of an arbitrary collection of closed sets is closed. Okay, so it has three properties. Please remember. Now next is definition. Closure. Please pay attention. There is a closure of the set and closed set. Okay, closure set definition. Please pay attention and try to differentiate. Closure of E, denoted by CL of E or E bar, is the intersection of all closed subsets of R containing E. Okay, now you see, so closure of the set is the intersection of all closed subsets. You see, not closed sets, closed subsets of R containing E. In other words, if C alpha is a class of all closed subsets of R containing A, then closure of A is intersection. You see, intersection of C alpha. So another word, I can say, look, and by the example, I will try to explain. So actually, for given one set, set, I can say like this: closure of, for example, A, or for the given one set. So it is a set A, then union A prime. A prime is accumulation points. Okay, this is a closure of the sets, and closed sets, closed of A is a set of all. I can't say that this is just A prime. You know, it is. Closed sets if it contains all its accumulation points. Okay, closed set if it is complement is open. You see, in the closed set, I cannot give this way the formula. Please, if you try to, I will explain with some example. Okay. Currently, closed of A is a set such that complement of CAC is open. If complement complement of A is open, then it is closed. Okay, it is closed. So this theorem says if R subset F of R is closed if and only if F contains of its accumulation points. You see, so in the closed set, accumulation points is included there, but in terms of finding the closed set, we need to compute just complement of A. Okay, how to compute the complement of A? We have the technique. So let me show the one example and clearly show that what is a closed set and open set. You see, the next interesting point, this is not example actually, this is a statement. Prove that A plus A prime is closed set. A plus A prime is closed set. But A plus A prime is, I can say it is a closure set as well. A plus A prime actually is a closed set. Where is the formula? And because this one is an intersection. Here union. Here intersection. Closed set is a closed of A is the intersection of C alpha. If C alpha is a class of all the closed subsets, you see, closed subsets of R containing L, then closure of A is the intersection of C alpha. The closure of E, denoted by this, is the intersection of the closed subsets of R containing E. Actually, this is the definition of the closure set. Closure of E is the intersection of all closed subsets of R containing E. But this statement is actually closed set. Can I say it is a and in A prime? A prime is a set of accumulation points. Usually we use this one. Absolute closure is a closed closure of A is a closed set, since it is the intersection of closed sets. Intersection of closed sets, then it is closed. Because you know here this theorem says the intersection of any arbitrary collection of closed sets in R is closed. So closure sets is a collection, is the intersection of all the closed subsets of R. So okay, let me so F is closed set and A is a subset of A of F, then A prime is derived set. This is the set of accumulation point is a subset of F. This is a theorem. Okay, I think here in this lecture actually not provided many examples. I think so we have to put some good examples to show the differences of the closure set and closed set. Closure. So this is a closure of E. Usually we say A union A prime is closure closed set. This one not closure, closed set. In here, actually, in here it is said A and union, then A prime derived set is closed set. Is closed. If I say this one C, so this A, this is closed. Because you know that in the closeness, we should add all the accumulation points and itself A together. Actually, always is closed set. So if I say here another examples, okay, now look, where is the differences between closure and closed set? There it is not stated here. Example, actually, we can check from examples for closed and closure sets. Closure sets. Closure set definition and so on. Closed sets. Closed sets, interior. Okay, I think this one. Okay, good. So you see, closed sets, interior closure and boundary. This is regarding to topological, little bit more general case. So the set A is closed if the set X minus A is open. X minus A is open. For the closed, this is actually complement. This is if complement is open, then X is called closed. It is the same definition as we know. The closed interval, for example, is a closed set. You see, this AB is a closed set. Since R minus AB, which is this, is open set. Another example, recall that U is a subset, is an element of tau ZA, the Zariski topology. I don't know what is the Zariski topology. Okay, example, if X is a topological space with a discrete topology, then every subset A is closed in X, since every set X minus A is open. So for the closeness, always we deal with the complement, the set X and empty set are closed. If AI is a closed set, then any arbitrary of the intersection of AI is closed. This is our theorem. Closed sets, then the finite number of union is closed. Okay, so this one is our theorem. Where is the example? We said that this is actually the sequence is convergent or not. Actually, this one for the topological sets, actually. For the topological sets. Okay, example. So this one little bit high level, but generally consider this interval. So interior, this is interior. This Y bar, you see Y bar, collection of all accumulation points is actually bigger than the interior point, the whole interval. Boundary is only the endpoints. This is actually a good example. So interior boundary, for this case, where is the Y? This is a Y. This is the interior of the Y. This is closed of Y. Y bar is a closed, and boundary of Y. Okay, actually, I think this one is quite okay. Nice example is given. So let us back to our class. So in this definition, the closure of the set E is an intersection of all closed subsets of R containing E. Okay, that one we understand like this. So as a formula, closure of A is the intersection of all CA. Okay, all intersection of all CA. So under this condition, we can prove that if F is a closed set and A is a subset of A, then A prime is also subset of A, of F. So how can we prove? This is a tutorial. Is closed set.
Doctor,
Yes.
I haven't seen how to difference between the closer set and closed set.
Yeah. Okay. Let
From
me.
the
Therefore, I am
example
searching
just
the.
now.
example. Okay, let me construct myself example. Okay, you will see the difference. Closure and closure set. Okay, so let me construct the example. Okay, so look, let A is given as, for example, interval 0, 1. Okay, like this. Now I want to find closet of A. Okay, I will put closet. This is fully of A. To find the closet of A, I should find the closure of A first. AC. I will find AC. What is the AC? Of course, this one is a subset of R. So R is our universal set. Correct? It is universal set. So AC is from minus infinity up to 0. Since 0 here not included, I will do like this. Okay? And union, 1 is included here, 1 to infinity. Okay, this AC. Can I say this one is open? Can I say this one is open set? How do you think?
Open.
You see, this set is not open set, is not closed set, AC, the complement of AC, because this part is open set, but this one is closed set. So union doesn't give anything. It is not open, not closed. Okay, not closed. It means this set, I cannot say it is a closed. This set actually not closed, not open. Okay, now I will find closure. Closure of A. Closure of A is in the closure, we say that intersection of all the closed subsets of R containing E. So if I take all the accumulation pointers, including the A, so the A union A prime, so it is 0, 1 plus 0, 1 including, it is becomes 0, 1. You see, closure of A becomes closed. This one is closed set. A itself is not closed, is not open. But closure of A is closed. Did you get the idea? So only, but here this formula is not given, you know. So that's why I'm. This one is always closed set. I have proven that this A plus A prime is closed set. For this case, it is like this. But this one, this formula, you know, is not given as a closure of the set. Closure of the set here saying that in the intersection of all closed subsets of R containing E. Okay, so for example, according to this definition, how can I compute in this form? Okay, this one is closed, is correct. Now, according to this definition, intersection of all closed subsets of R containing E. So it should contain E. For example, if I take intersection of all closed subsets of R containing E. For example, I can say minus 1 and plus 1. intersection, I'm just taking two sets with the closed form, okay? And second one is 0, 0, and 1. Okay, what will happen here? So from -1 up to 1, I have like this, and from this is the first set. Then second set is from 0 to 1, like this. So from here, if I take the intersection of these two sets, it becomes 0, 1. You see, closure of A is the intersection of all closed subsets of R containing E. So you see, this -1, 1 contains E, and it is closed. 0, 1 is also containing A. For example, I cannot, another set, if I add like this, not containing E, it is not correct. The intersection from 2, for example, 3. So this 2, 3 is a closed set, but it is not containing A. So this one I cannot do it. Understand? So please pay attention. Closed set, actually, usually we calculate the closure of the union of A prime. A prime is all the accumulation points. That one is easy. This one is very convenient formula. You see, this one also gave the 0, 1. This one is also gave 0, 1. So given set is not closed set, but closure of A is a closed set. So this one is closed set. Understand? Difference with this example? Any questions? I think now it is clear, right? Closure?
So closure must be closest, but closed not always closure.
Yes. Closed is not closure, but closure of the A is closed set.
Okay, thank you, doctor.
That is the main point. So now look, actually, so this one, as I said, that this is a formula for computing of the closure of the set. And this is a proof because here, how they want to prove? They are taking X from the complement of this, and if taking the complement of this union, of course, it is not belong to the A prime, right? So if not belong to the A prime, there is a epsilon A intersection with this, except X is empty set. What is this? This is a we have isolate. This is not isolate point. This is a accumulation point, set of all accumulation points. So this one says that A intersection with this is empty set or gives only X. However, the A intersection of this is empty. We also claim that A prime with this is empty, and this is also empty. Hence, there is a delta such that is a subset of this, and this one is empty. So Y prime, Y is not belong to the A prime, and so A prime intersection with this is empty. So in that case, this one belong to the complement. If belong to the complement, this one is a open set. If it is open set according to A prime C is open set, and therefore this set is a closed. You see, they are trying to prove the complement of this set is open set. If complement is open set, then according to the definition, this set is closed set. Okay, the proof little bit complicated. Actually, maybe next time I will give more simple proof of this. Now, you see already here, the closure of A is a union of A and it's all accumulation point. Now, you see here exactly the formula is given here. So actually closure of A is easy to compute. Finding the closed set, we have to go to the complement of A. Then if complement of A is open, then we say it is closed. If complement is closed, then it is open set. Okay. Now another interesting formula. Actually, it has two formulas. Interior for the closure of A, we have the two formulas. One, easiest one is like this: A union A prime. Second formula is the interior point of A and boundary point of A. This is also very good formula. You know, for straight line is easy to see, but for two-dimensional, three-dimensional, and n-dimensional cases, usually we use this one. You see, boundary of A include into the interior of A, then becomes closure of A. Okay, the two theorems is a good properties of the closure set. Okay, so the proof is not given here. The next theorem gives the substance. Actually, this one we need to for this one is given the proof. For this one, no proof. Important one actually the Balzani-Weierstrass theorem. Every infinite and bounded subset of R has at least one accumulation point in R. You see, infinite and bounded set of R has at least one accumulation point in R. Every infinite and bounded set. You see, infinite and bounded set. How we can understand that set is infinite and bounded? Actually, this one, the Balzani-Weierstrass theorems is very important in the sequence. Here for every x, all the proof of the theorem I will prove next time. So what about the last one? This example. Let P be any number, then each closed interval with center P, this is center P, correct, is a neighborhood of P, since it contains the open interval containing P. Each closed interval is a neighborhood of P, since it contains the open interval containing P. So this example says that it is actually this one is a neighborhood of P. So this closed set is also neighborhood of P, including the endpoints. This one including endpoints. So neighborhood of P can be calculated in two ways. Please pay attention. Epsilon neighborhood of X in the R. This is the interval, open interval. We usually call it neighborhood of X. But this one is also use it as a neighborhood actually. X minus epsilon, X plus epsilon, including the endpoints, is also use it as a neighborhood. Okay, neighborhood. And the last one is a neighborhood of each point from 0, 1 is a neighborhood of each point, but 0, 1 is not neighborhood of 0, 1. You see, this example says that 0, 1, the closed interval, is a neighborhood of each point of 0, 1. But 0, 1 is not neighborhood of 0 and 1. Because, you know, in the neighborhood, when we subtract delta and add the delta, so this interval should contain the point of the set of the set. You see, for 0, 1, yes, this one is a neighborhood. But for for the 0 and 1 itself, the boundary for the boundary point, it is not neighborhood. Okay, to be neighborhood, when we cut out the point from with epsilon radius, so it should be in the set. It should be in the set. That one is called a neighborhood. Okay. Okay. Anyways, so the next week I will prove the Bolzano-Weierstrass theorem and give more examples on understanding of all, not only closure set, closed set, open set, closure set, complement set. So I will give a few examples and go to the next important theorem, which call it compact sets. This one actually more difficult than the previous one. Previous one actually is easiest one. So this one is little bit complicated one. But this is real analysis. We have to go through this and differentiate how to find compact sets, how to find open sets, how to find closure sets. Okay. So now closure is clear, very clear, and it has two properties. You see? So A plus A prime. A prime is a derived set. We add all the accumulation points. Another word, interior point plus boundary point. If we add these two, interior point and boundary point, we get closure of the set, not close it. But closure of the set is always closed because of this theorem. A union A prime is closed set. For any set, if you find the closure, you will get closed set. But if for given A, if you want to find the closed of the set, you have to find complement of A and show that complement of A is open. Then you can say that it is a closed. Okay, so that's the differences and very interesting. There is some difficulties as well, but in general, that is a case of the set theory. Actually, set theory is very interesting and sometimes quite complicated, but for real analysis, we always consider only real line. So that's why we can imagine very well. For the topological space, it is quite complicated, and there are a lot of theory which I also cannot understand well. Now, I think this time you are learning the topological subjects as well, right? Topological space you are learning, right? It is much more difficult than the real analysis. So we can discuss some topological problems with me. I am now reading the topology as well. You see, just now one paper, the notes is related to the topology, not the real line. So real line is a particular case. This particular case theory generalized for any high dimensional space. So that's why if you know very well all the concept of the real analysis, then you can easily extend this theory for any topological space. Okay, any questions? Today, one friend gave very good questions. You see, after considering the problems, we have seen that there is big difference between closure and closed set. Okay. Thank you very much. Do you have any other questions?
Excuse me, doctor.
Yes.
Can we get the schema for quiz 1?
Oh, schema. Okay. So in that case, I will put this answer scheme and results. Okay. So this
Okay,
coming Sunday for both quiz 1, quiz 2, and answer scheme. I will put in the pembelajaran. You can see there. And actually, for your answer scheme, I don't want to give. If you believe that you have something wrong in my estimation, you can contact personally. Okay. But In the personal contact, please be careful, because if I am wrong, no problem, I can add the extra mark. But if I write and give the extra marks, I will deduct the extra marks, because you are taking a lot of time for discussion of that problems. First, you see my scheme. Actually, here I have seen in your answer, from one side, I was happy. Some students solved the problem using different method than I have shown, and different than my scheme as well. But some students making wrong solution, wrong decision, actually. A lot of wrong decision because of wrong understanding the problem. Okay, 2-3 schemes I have seen. One, for example, for the first problem, the proof of, in order to prove, you have to put some condition. So that condition, most of the students didn't put the condition and just prove the theorems. Prove the statement. It's not statement, proof of the statement is correct, but there is no condition. Therefore, nobody get the 10 marks. So you will see, if you really see my scheme and your scheme and is the same, and you get the less mark, then please contact personally. Okay, I will consider sit together with you on the online and show you answer scheme and over there. But I usually always estimate from the above, not from the below. The little plus minus I will add, half marks, 1 marks, usually I add, not estimating below. But for the proper one, like who get the 9, I didn't add any marks, because that one is really full marks. Okay, that's all. Thank you very much. In that case, now it is Azan time coming. Thank you. Bye bye.